Good morning. Excuse me. Happy Friday. Happy end of May. Crazy. Here is the answer key to the problems I'm going to post today. Is actually going to match up this time. I realized as going through your work yesterday that the video I posted was not the problems that meant to go up. There was a mix-up. That's my bad. But this one will make sure it works. So here we go. All right. So number one, a person lifts a 2.5 kilogram book from rest from the ground to a height of 5 meters. At this point of 5 meters, the person has moved the book at 5.1 meters per second, moving it up. What is the average force the person applied to the book? Okay. All right. So we need to find force. If we look up here at all of our equations, let me get out the old pen. That's what I have to look at because that has force. So one has force in it, so we're gonna have to use this one. So if we look at this one, we don't have an angle, so we don't need that. So in order to find force, we need to know work and we need to know distance. Well, we actually have our distance already. It's 5 meters. The only thing we don't have is work yet. So looking through, I want to figure out how we know what work is. If we look at these two equations right here, this is the one we're going to look at. This is actually, we wrote it down like this in the notes. Work equals delta K. Work equals the change in kinetic energy. So that's really the equation we're going to use. All right, so to find work is half of 2.5. And then it's V squared minus V naught squared, or 5.1 squared minus 0 squared, because the initial velocity is 0. So if we do that real quick, so 5.1. Not very quick with the old phone calculator. All right. Uh, 32.5. So that is the number of joules of work that this person is doing. So if we plug into here, 32.5 equals force times distance. We know the distance is 5 meters. If we divide both sides by 5, we get 6.5 newtons equals force. All right, that is question 1. All right, question 2. So we have a pendulum swinging back and forth. How fast will the pendulum be moving when it reaches the bottom of its path if it started from rest? So it's here and it's going to swing like this, follow this parabolic path down here. So that's A. And then B, how high it would make it up? It loses 12% of its energy during its swing. Okay. So this is a before and after type problem. So we have, we're going to use the law of conservation of energy here. All right. So let's think initially. Well, initially, it's at its highest point, so we know it's at rest. So there is no kinetic energy initially. All of the energy initially is going to be potential energy due to gravity. Okay, and then at the end of the problem, it's at its lowest point. So the height would be 0. There's no potential energy due to gravity. It's all been transferred to a kinetic energy. So now we can plug our numbers in. All right, so M is 3.5. That tells you at the bottom. It's right here, 3.5. All right, mass times M. Oh, I'm doing backwards. 8.9, that's H, and then 9.8 is G, equals 1/2 mv squared, or 1/2 of 3.5 v squared. All right, so again, let's solve this. So on the left-hand side, 3.5 times 9.8 times 8.9, that's 305.27. And on the other side, we have 3.5 cut in half, that's 1.75 v squared. All right, so now we'll do 305.27 divided by 1.75. And then we'll take the square root, 13.2. So at the very bottom right here, V is 13.2 meters per second. Okay, all right. All right, see, for part B, how high would the pendulum make it back up? So we could make this like a really complicated problem. We could do before the energy and solve for it and then get rid of 12% of it. And that's a real convoluted way of doing the problem. There's a much easier way of doing the problem. We have to use concepts here. Let's think this through. All right. If there was no energy lost, okay, this would swing all the way over to here to a height of 8.9 meters. Okay, it can't swing above 8.9 meters because that's all of the energy it had. It could only go to a height of 8.9 meters if gravity's the only thing propelling it back and forth. That's why the first hill of all roller coasters is always the biggest hill. It's like a gravity roller coaster because that's where all of the energy for the ride comes from. So same idea. You can't get higher than 8.9 meters. All right. Well, if we lose 12%, that just means our height is going to be 12% smaller than 8.9. It's just going to go up that much less. So all we can do, you do 8.9, okay, times, and we're going to multiply by 0.88, because if 12% was lost, that means 88% of the energy remains. So if we do 8.9 times 0.88, you get 7.84. Actually, it's 7.842, blah, blah, 7.3 meters. Okay? So 1 second. Sorry that we don't know where Rebel's pup tag is, but good job playing with your color forms and making good pup tags, man. You're doing awesome. Pound. All right. 3, a ball mat, this is a pretty big one. A ball with a mass of 2 kilograms is placed on a vertical spring, so that means the spring is like this. Press that way. K is 1,300 newtons per meter, and it is compressed 1.7 meters. Make this initial compressed height 0. A, how fast is the ball moving when it leaves the spring? And then, oh, you might think about the height at this point. Okay, and then we'll look at B. So this is going to be a conservation of energy problem, so that's this big equation down here. Okay. But, all right, we're going to be able to shrink it a lot as we talk this through. All right. Okay. Well, initially, the ball is at rest. Okay, so there's no kinetic energy initially. And since we're going to make that initial height 0, there's no potential energy due to gravity. So all the energy in the beginning is actually potential energy due to elasticity. Okay. All right. However, on the other side of the equation, all right, now that we're 1.7 meters in the air, we are going to have a potential energy due to gravity because we're no longer on the ground and we're moving. All right, there is no elastic energy because the spring has done its work already to propel the object 1.7 meters in the air. So the spring is no longer relevant, so we don't have to worry about potential energy due to elasticity. All right, so now we're just going to play everything. So potential energy elastic is 1/2 K. All right, K is 1,300. All right, and then how far is it compressed? 1.7 squared. Okay, equals mgh 2 9.8 times 1.7. All right, because that's how high it is in the air. All right, plus 1/2 of 2 v squared. All right. Hey, Buddy, make sure you pick up your color forms. They're all over the ground. So 1.7 squared times 1,300 divided by 2. So this becomes 1,878.5. All right, equals 2 times 9.8 times 1.7, 33.3. Plus v squared, because half of 2 is 1. All right, so we bring that over to the other side. All right, and then take the old square root at 42.9 meters per second. All right, so the velocity in the beginning, 42.9 meters per second. That's A. Okay. B, how high above the equilibrium point, not where the height is 0 of the spring, will the ball make it into the air? Okay, so initially, all right, here's what we know, and we actually just kind of solved this. All right, initially, we have potential energy due to gravity because we're 1.7 meters in the air, and we're moving, all right, that's kinetic energy. And then at the very top, it's all gravity. All right, so mgh again. All right, we just wrote this 2, 9.8, 1.7 plus, I'm just going to write half of 2 is 1. I'm not even going to bother writing it. So it's just v squared, 42.9 squared equals on the other side mgh. So 2, 9.8, and then h. All right, this simplifies to 19.6 h. All right, and on the right side, let's see, got 1890. And I get right, so when you solve, you get 96.4. Okay, so that's how high in the air it gets from that point, okay? But how high above the equilibrium point, not where the height is 0. Yeah, it is 96.4. This isn't right. So don't worry about that last part. So 96.4. All right, 4, almost done. Okay, 1,200 kilogram car is driving down the road going 25 meters per second, and it slams on the brakes until it comes to a stop. If it took 39 meters to stop, what is the average force of friction? So this is actually just like number 1. So we're going to use the formula work equals 1/2 m, work equals 1/2 times m times, in parentheses, v squared minus v naught squared. Right, so work is half of 1,200, 0 squared minus 25 squared. Okay. So that's 25 squared times 600. Negative 375,000 joules worth of work. It's a negative work. Why is it negative? Because it worked against us, and when we solve for, we get a negative number. All right, that's work. Well, to find distance, or sorry, to find force. It's work equals force times distance. We know the distance is 39 meters. We just divide our answer by 39, right? And we get negative 9,615 newtons was the force of friction. Okay. All right. And last problem. 1 kilogram blocks is placed and pushed 10 meters with a force of 8 newtons. Friction removes 50 joules from the system. What is the velocity of the box after the 10 meters? Okay. So if we shoot back up here, we want to use this equation at the end. I know I have to actually have my pen annotate this. We need to use this one at the end, because if we know work, which we're going to get, and we know mass already, and we know the initial velocity was 0, once we know work, we can find v squared. Well, to find work, we can use this right guy over here. All right. Okay. Oh. So we have a box, and we're pushing it one way. All right. And we got the force of friction. All right. And we're going to basically turn them both into work. Right. So the net force, or actually not the net force, the net work would be work equals work push minus work friction. Okay. Well, work equals the pushing force. That's 10 times 8, or 80. And friction is 50. So the net work is 30 joules. Okay. Now we can use the equation work equals 1/2 mv squared, basically. So work equals half of 1 v squared. So we know half of 1 is half. And then we run that out to the other side by division. So that gets us 60. And we take the square root of 60 and we get 7.74 equals V. All right. So those are the 5 problems. I hope this helped you out. If you still need help, don't hesitate to ask. All right. Have a great weekend. All right. Bless you. You want to say bye? Bye. You want to wave? See you guys later. Have a great weekend.